My name is Hastings Greer, and I'm presenting the paper Inverse Consistency by Construction for Multistep Deep Registration. First, we're going to look at a traditional deep registration problem. We have two images that we're trying to bring into correspondence, and we have a transformation model of just 5x equals kx. That's a scaling. So the question is, what scaling factor can we apply to the moving image to bring it into correspondence with the fixed image? We can tell by inspection that that's about 150%, and the neural network should output 150% to bring them into correspondence. But there's another way we could look at these two images. We could say, by what factor do we scale image B to make it align with image A? And that's going to be about 66%, and we'd expect the neural network to output 66% for K in that case. But these two numbers have a relationship. When multiplied together, they should get 1. If they don't, that means one direction's wrong. And it's independently interesting to find algorithms that have this consistency property, that if you swap the images, swap which one you're registering onto the other, then you get the inverse function. So for this simple scaling registration problem, we can do this analytically. So if we have a transformation model 5x equals kx, but then specify k to be two calls to the neural network, one with the input swapped, subtracted, and then exponentiated, then that causes this cancellation that you can sort of do just symbolically in the bottom equation. It is always going to be exactly 1. It's always going to be exactly inverse consistent. The key insight of our paper is that this doesn't just work for scalar k, it works for the neural network outputting any Lie algebra, which can then be operated on as a vector space and then exponentiated to the associated Lie group. And the same laws of exponents apply, and so the cancellations still apply, and the approach is forced to be inverse consistent. So here we have that demonstrated for 4 Lie algebras and their corresponding Lie groups. So the Lie algebra of antisymmetric matrices gives rigid registration. The Lie algebra of matrices in general gives affine registration. We can have the neural network output a vector field, and then the Lie exponentiation operator in that case is the classic scaling and squaring operation. Or we could even have the neural network output a latent vector for an MLT, such as in NERF. In that case, the Lie exponentiation is integrating a differential equation. In all these cases, we just apply the formula from the math textbook and get a registration algorithm with this class of transforms that is, as you can see in the bottom row, exactly inverse consistent. For state-of-the-art performance, we can't do a neural network that just predicts the full transform in one scratch. What we need is these multi-step pipelines. For example, affine followed by deformable registration, or coarse deformable registration followed by fine deformable registration. To get that, we came up with this operator TSC that takes two existing inverse consistent algorithms and combines them into a coarse then fine algorithm that is inverse consistent. And the inverse consistency is proved by similar cancellations like we saw previously. It's just fairly direct operations on the symbols. This lets us do multi-step registration where the individual steps are any of this wide variety of registration algorithms and transform models that we proposed earlier. So here we have two-step inverse consistent registration and even n-step inverse consistent registration. This two-step registration, as can be seen in the dotted and dashed lines, accelerates convergence over the solid lines, which are single-step registration. But on top of that, we see that the inverse consistent approach actually converges faster. Even a single-step inverse consistent converges faster than a single-step traditional approach. This all works in the real world. So we applied to 3 data sets: brain registration, lung registration, and knee registration, and got results that are right up there with the state-of-the-art, but with inverse consistency error 10 times smaller than even other approaches attempting to do inverse consistent registration.